Welcome back to my channel. Today we are starting a new series on basic antennas for radio communication. We know that radio by itself cannot do anything. Radio produces radio frequency signals, but in order to get transmitted over the air or space, you need antennas. Without antennas, if you have a radio alone, it cannot communicate with another radio located somewhere else. The commonest radio frequency equipment which all of us use is the mobile phone. It works in the ultra high frequency. Mobile phones in olden days had to have antennas on top of them. Some were having telescopic antennas, some were having shorter antennas, and then it became shorter and shorter. Now you don't see the antenna for the mobile phone. That's because it is within the printed circuit board. It is a small antenna within the mobile phone itself. Even now, satellite phones have external antennas. At the same time, the walkie-talkie used by law enforcement personnel and security personnel has a external whip antenna. Your car also has a whip antenna, or nowadays the newer cars have what is called as shark fin antenna. Shark fin antenna is not for a single purpose alone. That we'll come to later on during our discussion. So without antenna, a radio cannot function in its basic radio communication effort. We'll go into the details of different types of simple antennas first, and later on we'll learn more about difficult to construct antennas as well. One of the simplest antennas to construct for a beginner is a half-wave dipole antenna. Half-wave dipole antenna means, suppose this is half wavelength of the radio frequency wave, then if the antenna is fed in the center, each side will have quarter wavelength. That is the half-wave center-fed dipole antenna. It is the easiest to construct. Let us see how we do that. We can take, suppose this is the up to this quarter wavelength and another quarter wavelength to this side. So each one is quarter lambda. Lambda is the symbol, that is a Greek letter. It is the symbol for wavelength. Wavelength means wavelength of the radio wave in space or air, whatever medium of transmission it is using. The wavelength will vary depending on the frequency and the speed. Speed is usually the speed of light, 3 lakh kilometers or 300,000 kilometers per second in free space. In conducting media, it will be a little lower. The ratio is known as velocity factor. Suppose you are having a copper wire, it will be having lesser than free space, and that ratio is the velocity factor of the copper wave. So taking into consideration the velocity factor also, you will calculate the half lambda in that particular medium. If you are making it of copper wire, you will have to consider the velocity factor of copper wire, and if you are using aluminum wire, same. So you have two half wavelength, and this is fed to a feed line, and the feed line can be different types. Commonest we use is a coaxial cable. Coaxial cable will be something like this. There will be a central conductor and an insulator after that. Then externally there will be a shield, and outside the shield there will be a sheath also, protective sheath. That is coaxial cable. And suppose you are using a coaxial cable, one of the elements can be connected to the central conductor and the other element can be connected to the shield. This is representative, and it goes down and then it goes to the radio. That is the basic schematic of a simple half-wave dipole antenna which is quarter wavelengths to either side. And this is a balanced antenna. And the conducting line, that is a feed line, which is if it is coaxial cable, it is an unbalanced feed line. That we'll discuss later on because the theory involved is a little more difficult to understand. But for the time being, understand that coaxial cables are unbalanced feed lines. Half-wave dipole antenna is a balanced antenna. Radio is also unbalanced. When you are connecting an unbalanced feed line to a balanced antenna like dipole antenna, you need something known as a balance to unbalanced in between. That's a transformer. It's an impedance transformer which is connected between these two. So ideally it should not be connected directly like this. There should be something known as a balun. Balun is here. The most commonly used in this region is 1:1 current balun. There are voltage balance and current balance. Here we need a 1:1 current balun. Coming back to this quarter lambda. Suppose you are operating on the 40 meter band. Then quarter lambda will be 10 meter. This will be 10 meter and this will be 10 meter. That is the most popular amateur radio band. Suppose you are using the lowest band, 160. Then this will be 40 meter long. You can imagine how long the antenna will be. It will be very long. Most of us are not able to make a 160 meter antenna. 80 meter, it will be quarter wavelength, will be 20 meter long. And if it is 10 meter, it is much more easier. It is just 2.5 meter to the other side. Now coming to VHF, 2 meter is the popular VHF band. That is 2 meter. Then this is only 0.5 or 50 centimeters to either side. And if you go to UHF, it is again 1/3 of that because VHF frequency is 70 centimeter. Now when you have a balun and feed line here, it's a bit heavy. So this dipole will sag downwards. Central portion of the dipole will sag downwards. So what can you do for that? You can keep a pulley here. And you can keep a weight here. A pulley and weight mechanism can be used to balance the position of the antenna. If the weight is increased, then you can have a straight antenna, dipole antenna. And in case of antennas, height is might, meaning that the higher you take the antenna, better the performance. You might wonder why mobile phone does not have any of these things. That is simple. Mobile phone is not transmitting from one mobile phone directly to another mobile phone. It is going through the network. Your signal from the mobile phone need reach only the nearest mobile tower, which has a splinted antenna, usually at a much higher location. So mobile phones do not need high antennas. And in regions where mobile signals are poor, like places where towers are not very frequently found, then people use external antennas and boosters and everything for having a good mobile signal. There is another variant of this half-wave dipole antenna which is more popular because it requires lesser space for mounting and lesser number of supports. I'll show you. Suppose there is an inverted V antenna. This is an inverted V antenna. Inverted V antenna. Again, each side is quarter lambda only. The angle here may be around 120 degrees. It can vary within a limit depending on the location where you are using it. In case of usual horizontal dipole antennas, you need two supports at both ends, high supports. You can have two trees, but if there is plenty of foliage of the trees, they can act as radio frequency absorbers and decrease the performance. A lot of trees is not good for radio communication, and a lot of buildings around is also not good because they will block radio waves to some extent depending on the frequency. Certain waves go straight to the sky and back, then buildings may not be a problem, but line of sight communication like VHF, blocking of buildings and trees are not good for efficient communication. And in this case, you need only a single high support, but the lower supports can be in the garden. Suppose you are mounting it in a home, the central support can be on top of your home, and the two supports can be poles on the ground. But even then you have to be having a little caution. These ends should not be accessible to people or animals or children, because that can give radio frequency burns. You know, radio frequency current does not give a usual shock. It produces skin burns which are very difficult to heal. So these ends should be significantly high, not to be accessible to animals or human beings or children. And ideally nowadays we use only insulated copper wire. Long back we used to use uninsulated copper wire, but now we use only insulated copper wire, especially for inverted V. The ends are lower down. Now we'll go into the current and voltage in a simple dipole antenna. The current will have a maximum at the feed point. That's the maximum point, and minimum at the ends. That is, it's a sine wave, and half lambda means half of a sine wave. So maximum will be at the center. Voltage is on the other way around. Voltage on the antenna is minimum at the center. These two are out of phase. That's why ends of the antennas, in case of dipole antennas, have high voltage, especially when the radio transmission power is more. Both ends will have higher voltages, while current is highest at the feed point. That is the basic principle in half-wave dipole antennas. Gain of antennas is measured with reference to a spherical isotropic antenna, theoretical antenna, that will radiate all around in all directions. That is the theoretical isotropic antenna. In case of dipole antenna, it has some directional nature. This dipole antenna radiates in the direction both sides of the dipole. Towards the ends, the radiation will be minimal. That's why it has some directivity. And suppose you are keeping the antenna north-south, then this is the way that the signals will pass. It will not pass towards the ends. That is the directivity of dipole antenna. And the gain with respect to an isotropic antenna or theoretical antenna is 2.15 decibels. That is known as dBi, gain with respect to isotropic antenna. And there is also another term, gain with respect to dipole. If you take dipole as the standard, then only gains above 2.15 decibels will be taken as gain. That gain is mentioned as dBd. Usually the highly directional antennas like Yagi antenna or Moxon, all those antennas will have gain more than the dipole. That's by adding more and more elements. Then they can have both dBi, that is gain with respect to isotropic antenna, or dBd. The difference between these two gains will be 2.15 decibels. Hope you have enjoyed this basic session on antennas. We'll discuss more antennas in future, starting from very simple ones to more complex ones.